All right, good afternoon, everybody. My name is Kegan Heaney. I am an applied physics and mathematics major from the University of North Carolina, Charlotte. My mentors were Dr. Peter Lee and Dr. Shreyas Balachandran. And my project was to see if we could correlate uniaxial tension, tensile stress with microhardness in annealed copper 101. And we actually found out that there is a linear correlation on the samples that we tensile stressed and then compared the micro hardness in annealed copper. And this is extremely useful because this could allow us to predict the maximum stress reached in magnets and other components when doing autopsies or trying to review why those components failed by simply measuring the copper hardness. There we go. Okay, so to give you a little bit of background on why we're doing what we're doing, first, the image in the top left-hand corner, that's a computer-generated image of a large, one of the dipole magnets from the Large Hadron Collider. And this part right here, the superconducting coils in figure 2A over here, you can see a close-up. And basically anytime in any experiment, but particularly with the particle accelerator, anytime a component breaks, it's extremely important to determine, why did that component fail? And so they do what they call magnet biopsies. And my research actually came from a previous REU student's research where they were doing an analysis of an 11 Tesla dipole that had been damaged and trying to compare it to an undamaged coil. And you can see the image analysis right here with the little cracks in the niobium tin subelements in the copper. And they actually did a hardness test on a damaged coil, multiple hardness tests on a damaged versus undamaged coil. And you can see that the damaged coil had a much higher and wider range of hardness values compared to the undamaged coil, which were basically grouped together. And it also had a higher mean as well. And so that prompted the question of, can we correlate hardness with tensile stress? Because hardness tests, compared to a lot of the other testing that is done, is much easier. And so our process for this was we took 20 copper 101 tensile specimens and we subjected them to heat treatment just like they would for the niobium tin magnets. And then we performed tensile tests per ASTM E8 standards. And that's basically the American standards for testing of materials to make sure that anybody who's doing tensile tests and certain material tests, you're using the same standard, the same ratios. And so that way you can compare different tensile tests across different laboratories or experiments. Once we had strained the samples to certain points on the stress strain curve, we then cut from the middle of the gauge section and mounted those samples. Once those samples were mounted, we then polished them using the same procedures that the Applied Superconductivity Center at the MagLab uses for magnet autopsies in past studies and currently. And once they were polished, we then did microhardness testing, Vickers microhardness testing. And so you can see sample A is a tensile testing. You can see it starting the neck right here. B is where we're cutting the samples, sections of the samples. C, this is actually the hardness testing machine. And basically what it does is it puts a little indent in there. It has a diamond indenter. Image 3D is actually what you see looking down the microscope when doing the hardness testing. And it'll measure the diameter and return a hardness value. And so what we found was, on the left-hand side, you can see the stress strain curves for the samples of copper 101. The first 3 samples we did as a failure test to actually get the entire stress strain curve and to make sure that they fell pretty much on the same curve, which they did. So once we knew we had the right stress strain curve, we then took our samples and plotted them to different points, as you can see right here, from 25 to 150 megapascals. Once that was done, like I said, we then mounted and did hardness testing. And we then plotted the hardness testing value against the stress that sample had received. And I was quite surprised by this, though my mentors were not. but there's actually a linear trend going on here based on the samples that we did, to the point that we can even get an equation for hardness value in terms of tensile stress, which, as you can imagine, would be extremely helpful when doing these magnet autopsies. If you can just do a hardness test on it and get an idea of the approximate stress that component underwent, you can determine, do we need to build better components? Was it, a different issue? Is this a one-time thing, or do we need to make our components stronger? So this is huge because now being able to correlate Vickers hardness to uniaxial tensile stress, what we found is if you're within a 5 megapascal window, resolution window, it's hard to tell. So the difference between 25 and 30 megapascals, they were almost identical when you factor in standard deviation. But as you move higher, it is linear. And so, as I mentioned, this can not only help determine the stress in the current magnets that we're using, the niobium tin, but this procedure here could be applicable to pure dilute alloys. For instance, there's future, next generation magnets using silver Bi2212 magnets. This procedure might be applicable for there, for that type of material as well. And so next steps, we want to do more testing on the curve. So we did plot the curve, but there's other spots on the curve that we could test. We'd like to do some image analysis using the scanning electron microscope to see if there's any difference in the grain. And then potentially we could create a database with sets of correlated data for magnet autopsies. So when a component breaks at CERN or wherever, they're using copper 101 with their components as a device for thermal conductivity, they can just do a hardness test, go to the database, match it up, and say, okay, this was the maximum stress that this component underwent. What's interesting to consider is, can we do this for other elements? I think that would be a fun project to do in the future, to see if other elements or alloys have a linear correlation as well. And then also a systematic review, just to kind of refine our process and see what could we do better, which I think is always a huge part of science. And then I also just want to give a special thanks to Dr. Cooley, Bob Walsh, Bill Starch, Leo Loris, Abigail Williams, John Teetsworth, and Brenham Chanel, and everyone at the MagLab, Kawana especially, for this summer. It's been a great experience. Thank you.